Welcome to Mahjong Maths, where we explore the maths of Mahjong. Today, the 13 Orphans, otherwise known as Kokushi. What are the 13 Orphans? When should you go for them? And just how likely is a 13 Orphans setup? What are the 13 Orphans? The 13 Orphans is a Mahjong hand consisting of one of each terminal tile, each dragon, and each wind. Note that there are 13 tiles here, hence the name, plus one duplicate. This hand is worth 32,000 points for a non-dealer in Riichi, 64 points in Mahjong competition rules, or any number of values in other variants of Mahjong. When should you go for 13 Orphans? Amber at pathofhorror.com did an interesting analysis of Kokushi completion rates for horror players. These are very skilled Riichi players on an online platform named Tenho. While I recommend that you read a blog post, which I've linked in the description below, the biggest takeaway is that having at least 11 unique orphans in your hand is the cutoff at which 13 orphans becomes mostly viable. Depending on the exact variant you play, the point of viability might go up or down. Variants with a larger point differential between the 13 orphans and a normal hand, which is about 6 times in Riichi and MCR, and slow hand formation might justify a 10 orphan attempt, while a particularly fast variant with a low point differential might necessitate 12 orphans. Just for fun before we move on, let's suppose that your opponents have literally no idea how to play Mahjong. They discard tiles at complete random and will never complete a hand. What's your probability of completing the 13 orphans? You can think of this as an upper bound to how probable it can possibly be for you to complete the hand, even the best of conditions. I wrote a simulation, code linked below, to find out. After 10 million games, here are the results. In short, anything below about 9 unique tiles is a fool's errand, even the best of scenarios with the dumbest of opponents. How likely is a setup? There are tons of estimates for the probability of a setup online, but I've never seen someone do the exact maths. As the massive nerd I am, that struck me as an invitation. First, here are the results so you non-nerds can scurry off. Good setups are very, very rare. You're only going to get a setup worth playing about 1 in every 70,000 hands, and the chance of getting a full 13 Orphans draw is about 1 in 3 billion. So unless you live to about infinity, you're never going to see one of them. Okay, results over, let's nerd out a bit. On the left-hand side of the table, you see that I calculated the number of possible hands for a given draw. This number is exact. Here's how I figured it out. Combinatorics. Let's call the 13 orphan tiles T1 through T13. First, let's fix the exact number of each of T1 through T13 that we have in our hand, and figure out how many possible combinations that gives us. For those of us who know a bit of combinatorics, that's nice and easy. For I equals 1 through I equals 13, we multiply 4 choose Ti to get the total number of ways to choose our orphans. And then we multiply all of that by 136 minus the sum of T, choose 14 minus the sum of T, to get the number of ways to choose the rest of our tiles. Then, to find the number of ways to draw a 13 orphan setup with n uniques and with or without a duplicate, we just sum this over the set of all t's with n non-zero rows, and with or without any numbers above or equal to 2. Unfortunately, there are a lot of possible tuples t to try. Thankfully, lots of those tuples are the exact same as some other tuples, just permuted around a bit. 1, 0, so on to 0, for example, is the same as all zeros and then a 1, just in a different order. We call this an equivalence class, since both of the tuples represent the same type of 13 orphan setup, just with a different orphan. Note that 2 separate equivalence classes can represent the same type of setup. 2 and then all zeros, and 3 and all zeros, are both in a different equivalence class, but still both represent a 1 plus 1 setup. To reduce the amount of computation needed, we're just going to look at each equivalence class once, and then multiply by the number of elements in that equivalence class. The number of elements in a tuple's equivalence class is equal to 13 factorial over the number of zeros factorial, number of 1s factorial, number of 2s factorial, number of 3s factorial, and number of 4s factorial. So now our maths looks like this. Num hands for an equivalence class T is equal to 13 factorial over all of those factorials, multiplied by that product that we took above. Finally, we enumerate all the possible equivalence classes, we get the number of hands in that class, and we just assign them to the appropriate setup, like 1 plus 1, or 5 plus 1. To enumerate all the equivalence classes, we can generate the set of 13 long tuples, which are 1, strictly decreasing, 2, have sum smaller than or equal to 14, and 3, have integer elements between 4 and 0. Generating these is a simple exercise in dynamic programming. If we call the set of equivalence classes that correspond to a setup SES, then our final equation looks like this. Numhands S is equal to sum of T and ES multiplied by that massive equation we have above. I wasn't able to find a closed form for this equation, but if anyone's even nerdier than I am, I'd love to see a solution. Thanks for watching, especially if you watched that nerdy segment at the end. Feel free to comment below if you have a favourite hand, or especially Yakuman that you'd like to see analysed. Mata ne!